Hi there. So right now what I'm going to do is talk about section 5.3, and then this will complete our chapter with logs. So this is about our log function and some applications. Now, to begin with, we're going to graph our log function. And again, I don't want you to stress about, memorizing things. I just want you to get an idea as to what these graphs look like and the behavior of them. And then after that, what we're going to do is a few different applications of our logarithmic functions and where they're used. I do want to tell you that don't worry about memorizing any formulas. Any general formulas that you need on a test, I will give to you. Okay? So, our first goal is to graph our log function. Now, what I would like to do, just to reinforce what we've already done, is first graph our general exponential function. Okay? So, our general exponential function, we've already graphed him, and you'll recall that what we had is a general graph that looks like this. Okay? Goes through the ordered pairs 0, 1 if you just have a number 1 in front of your base. Okay? Now, what are some properties of our exponential function? We saw that our domain was all reals. Remember, your domain are the values you plug in for x. There's no limitations as to what we can plug in for x. We can plug in positive numbers, we can plug in negative numbers. Remember, if you plug in a negative, it just moves it to the denominator. And additionally, we can plug in 0. So we have no restrictions on our domain. Our range, we can read from this graph, it goes from 0 to infinity. Notice an exponential function is never actually equal to 0. It just gets super duper duper close to 0 as our x values get small. Okay? There is no x-intercept. This graph never touches or crosses our x-axis. We have a y-intercept of 0, 1 when we have a general exponential like this. If I had, say, y equals, who cares, q times a to the x, then our y-intercept would be 0q. Okay? And the other thing that we saw is we saw that as x goes to negative infinity, in other words, as x gets really super small, our function approaches 0. Okay? Now, we said that this is a horizontal asymptote because remember, you have a horizontal asymptote if as x either gets really large and or really small, your function values approach a certain number. Okay? All right. Now, why did I show us the graph of exponential functions? Well, because I'm going to use that graph in order to graph our logarithmic functions. How, you might ask? I'm going to use the fact that these are inverse functions. Okay? So, recall the following about inverses. You'll notice as we talk in this class, I go back to inverse functions very frequently. They're a really important concept. Okay? Let me just show you this. Suppose this is the domain of my function, and this is the range of my function. Okay? My function f takes the values in my domain to the values in my range. Inputs, outputs. Okay? Now, if I've got the inverse function, remember, your inverse just undoes whatever your original function did to begin with. Okay? So it takes these points here in our range of f and brings them back to our starting point in the domain of f. But notice these are precisely the inputs for my inverse function. In other words, the range of our function the outputs of our function are precisely the inputs of our inverse. And in a similar manner, these are the outputs of my inverse. So the domain of my function is precisely the range of my inputs. Okay? One of the other things that I mentioned to you is if the ordered pair AB lies on the graph of F, then the corresponding ordered pair BA lies on the graph of F inverse. Okay, again, why? I know I'm reinforcing this a lot, but it's a really important idea. Okay? Oops. We say that our function F takes A to B. Well, what is the inverse going to do? It's going to take B back to A. In other words, B is my input, A is my output. Okay? So, a beautiful thing to note when you're dealing with inverse functions is you're just bebopping the ordered pairs. All right, having said all of that, let's do this. Okay? Let's just take a general log function, and what I'm going to do is write out what my domain is, what my range is, what my x-intercept may or may not be, as well as what my y-intercept may or may not be. Okay? Remember, the domain of a function is the range of the inverse. So if we think of this as our function, the domain is all reals, that's precisely the range over here. And in a similar manner, wasn't the range of our function equal to the domain of my inverse? The range of my function is the domain of my inverse. The range over there was from 0 to infinity, so that becomes my domain here. Okay? Key thing, you can't take the log of a negative number. This thing here, whatever you're taking the log of, cannot be negative. Okay? Next, we see that there is no x-intercept. In other words, there is no point of the form, we'll call it, say, A0. Okay? Well, what does that mean for its inverse? What that means for our inverse is there's no point of this form. In other words, just like there was no x-intercept here, there's no y-intercept for this guy. Similarly, notice the point 0, 1 lives on this guy. Therefore, for the inverse, we have the ordered pair 1, 0. All right. Now, because we're just actually switching our ordered pairs, one of the things that you'll see with practice is that the graph of a function and the graph of the inverse reflect about the line y equals x. But let me show you what the graph of our log looks like. Okay, we know it goes through the point 1, 0. We also know that we can only plug in positive values. Now, let's look at what went on over here. Notice as x got really small, my function values approach 0. Okay, so now let's reverse that for the inverse. In other words, for my inverse, as x goes to 0, my function values are going to get really small. And then you'll see as you plot points that that's how your function grows. Okay? If you graph these on the same coordinate axis, and then you drew the line y equals x, you'll see that, yes, in fact, they are reflections about that line. Okay? So what's important for me to communicate to you? That in general, this is what your graph of your log function looks like. Okay? It's important for me to have you guys know that you cannot take the log of a negative number. And then the other thing that I'm going to mention to you, which we'll get to again in chapter 11, is the following. Notice as x gets large, don't my exponential functions grow really quickly? They do. Here as x gets large, my function is growing, but notice it grows nowhere near as quickly as our exponential functions do. Okay? So, the last comment that I want to make is, notice here, as x goes to 0, my function here goes to negative infinity. We call that a vertical asymptote. We'll get more into asymptotes when we talk about rational functions. But notice here I said we had a horizontal asymptote because notice it's approaching something horizontally. This is a vertical asymptote because it's approaching something vertically. Okay? So, please have a basic idea of the graph and our basic information. All right. Now, when are logs used in the quote-unquote real world? Well, logs are used frequently in applications where magnitude plays a role. Okay? So, logs are used when the magnitudes of various things we're discussing have a wide variance. A few places is acidity of solutions when you measure the pH of solutions, when you measure a sound in decibels, and also when you measure how strong an earthquake is using the Richter scale. Okay? Now, what I'm going to do is just go through one example of finding our pH and then one example of decibels. Okay? For any additional examples, they're worked out in your textbook, and I certainly urge you to read through them. Okay? So, let me first talk about acidity. All right. Well, when you measure the acidity of a solution, what that depends on is it depends upon the hydrogen ion concentration. Okay? That's written like this. Okay? H is the chemical symbol for hydrogen, and with an ion, you're looking at an imbalance in there. Okay? It turns out that the higher the ion concentration, the higher your acidity is. Okay? There's a formula for this. The pH is negative log of your hydrogen ion concentration. Okay? You don't have to memorize this formula. That will be given to you, so please don't stress about that. Notice there's no base written here, so by default we know it's base 10. Okay? So, one question that I'm going to ask is the following. I'll write it over here. What is the hydrogen ion concentration of a solution whose pH is 8.3? All right. Literally, this is a plug and chug into the formula. Okay? Notice we're being asked, what is the hydrogen ion concentration? We're looking for this. Okay, if we're looking for this, we better be given information about the pH, and in fact we are. We're given that the pH is 8.3, and that's negative log of our hydrogen ion concentration. Can we solve this? Yes, we can. The first thing that I would do, just like I isolate my exponentials, is I'm going to isolate my log. Okay? In other words, I can think of it as multiplying or dividing both sides by -1. So I'm going to get negative 8.3 is the log of our hydrogen ion concentration. Okay, how do you solve for what you're taking the log of? This is where you want to use that mantra. Change it to equivalent exponential form. Okay? How do we do that? Remember, you take your base raised to this power, and that's equal to what you're taking the log of. There's no base written, so we know it's a base of 10 to the negative 8.3 power is equal to my hydrogen ion concentration. And if you really want to compute this, we can do that 10 to the negative 8.3 power. It's really small, 5.01 times 10 to the negative 9th power. All right, so that was good practice for us. Again, why? Because it helped us remember that when you want to solve for what you're taking the log of, change it to equivalent exponential form. All right, the one other thing that I'm going to mention in this section is about decibels. Decibels are the units that we use to measure the level of noise. Okay? And here's the formula. Our noise level in decibels is equal to 10 times the log of I over I sub 0. Okay? Now, what do all of these mean? Well, again, our decibels is 10 times the log. Remember, that's a log base 10. I is the sound intensity that we're dealing with. And I sub 0 is this, what they call the standard benchmark. Okay? What is the standard benchmark? It's the lowest intensity that's audible to humans. In case you care, it's 10 to the negative 16th power watts per square centimeter. All right. Again, don't stress about this formula at all. Let me just show you a quick example. Okay? Suppose I tell you the following. Suppose I tell you that sound A measures 30 decibels and sound B is 10 times, or excuse me, is 5 times as loud as sound A. What is the decibel rating for sound B? Okay, well, let's compute this, and we're going to round it to the nearest decibel. Okay? How do we do this? Well, let's first deal with what we're given. Yes, in the end, we want to find the decibel level of sound B. But we're given information about sound A. So let's first discuss sound A, and then we'll discuss the relationship between sound A and sound B. So sound A, we know that that's 30 decibels. So 30 is equal to 10 times the log of I over I sub 0. Okay? Now, we're not going to be able to get very far here, but we will be able to simplify this enough in order to answer our question. First off, just like I had said to you before, like we isolate our exponentials, we want to isolate our logs. So what we'll do is we'll divide everybody by 10. And what we'll then get is that 3 is equal to the log of I over I sub 0. Okay? Next, let's get rid of our logs. How do you get rid of the log? You change it to equivalent exponential form. Well, no base is written, so by default it's 10. So I claim from there we have 10 to the third power is I over I sub 0. In other words, 1,000 is I over I sub 0. So from there, will you guys grant me that the sound intensity here that we're speaking of, I is 1,000 times I sub 0? All I did is get rid of my denominator. All right, we have now measured, or at least simplified a bit, given our information regarding sound A. Now, let's talk about sound B, okay? Why did I solve this for I? Okay, we don't know the sound intensity offhand, but the reason why I did is we're given that sound B is 5 times as loud, okay? Well, if sound B is 5 times as loud, don't we have 5 times I in that case? Let's go through this. So I claim with sound B, that's 5 times as loud as sound A, so it's 5 times I. Well, if I multiply the left side of my equation by 5, I need to multiply the right side of my equation. So that's 5,000 I sub 0. Okay? So, what is the decibel level for sound B? Well, that's going to be equal to 10 times the log. Well, what is my sound intensity? It's 5,000 I sub 0 divided by then I sub 0, right? We found I to be 5,000 times I sub 0. All right, well, we can certainly play with that. We have 10 times the log of 5,000. My I sub 0's cancel. And if you do those computations in your calculator, you'll see that we get 37 decibels. All right, that finishes up section 5.3. Have fun.